What I am going to talk about is, let's do the, okay, this is interesting. Okay. It seems to not do the presenter view, but the other view. There's always something funny going on. So this is me. I'm a Dutchie. I live in Amsterdam. And I've been in IT since 1989, hence the gray hair. But not much has changed, I think. The problems we run into are basically the same as we ran into 30 years ago. Only now you can, instead of, and this is what I love the most about my job at the moment. 95% of the work I do is in the cloud, mostly Azure. And the thing I love the most is that the last time I had a meeting with somebody from the SAN team to beg for terabytes of disk space is years ago. I don't do that anymore. I love that. If you're considering moving to the cloud, just the blob storage limit is 6 petabytes or something. You just create one and go. I'd love it. Who's running things in the cloud at the moment? All right, what, half of, no, more than half, okay, good. What I wanted to talk about today is, because if you run data warehouses in the cloud, you're going to one day or one way or another at some point run into the Parquet format, into Parquet files. And you might wonder, why should I use these things? What does that bring me? Is it the magical format that's super fast and always works? No. But is it good to use? Yes. But why? Well, I hope to be able to show you here why this is why this works, and also possibly knowing how it works, what's inside it, will make you understand what is a good use case for you and how you may even want to tune it or use it. Let's see if that works. I don't know. You tell me in the review afterward. There's a link in my last slide that you can tell. No, I didn't learn a thing, but honestly, the feedback that you give is really important for the organizers and also for me as a speaker. I haven't actually seen the feedback form, but if there's like numbers, you can say, hey, was he good or bad? Cool. Just click on the good thing. But if you feel that wasn't good, please tell me why. A bad grade I don't learn anything from that, but tell me why. Like, I didn't like it because I couldn't hear your funny, weird accent that you said you were Dutch, but you sound Scottish. I just couldn't make sense of it. I'd love to know. Let me know. Also, I'll keep an eye on the time as well myself. But, this is until exactly 6, right? Yeah, until exactly 6. So we're stopping at 6 because there's online people, and that's when the thing stops. If you have any questions, bring them on. Just blurt them out. Stop me halfway a sentence. All good. If you have something and you see something on a slide that you don't understand, or whatever, you don't have to wait until the end. There's no need. All right. This is actually not what we're going to talk about, but this is not in a Parquet file. I have a pretty simple use case for something that I used so far. This is a normal B-tree index in a normal database in a SQL server. And even if it's really big, I've had SQL servers, normal SQL servers, go up to 140, 150 terabytes that I was using with tables in it that had 80 billion rows. And because of the B-tree index, you could still, this is a non-clustered index. You could still, well done, you could still get to the row that you need, the one row that you're looking for, with a nice little simple B-tree index. You could just go where ID is X, and it would just find it really fast, even in a really big table. And I actually had one of these tables that had literally 80 billion rows, and a single query would take a couple of milliseconds. It was really good. And then you have a use case where, but I also want to search on another column. And that works. Just add another non-clustered index. Job done. The only problem was, so we're talking 140 terabytes SQL Server on an 8-core VM. If anybody, this is a rant on the side, this has nothing to do with the Parquet format, but if anybody ever tells you that SQL Server doesn't scale beyond X, find me, let's have a chat. It does. This works even in a VM. Anyway, so the problem I had with this was that second index that we put on, after testing it a bit, like, okay, we need this one, took 4 days. Like, create index, hit F5, you wait 4 days, right? This is, can I say what it was? I'm not allowed to say what it was. So I worked for a fraud department in a bank, so I'm not allowed to say what was in it. But it was 4 days to put an index on. And also, I had to have a meeting with the SAN people. Can I have 20 terabytes, please? Because I want to put an index on the thing. So at some point, we decided, okay, it works, but it doesn't scale well, because what happens if we need another index? And every index you add, the inserts are going slower and slower and slower. And it was also important that the system stays up to date. So we moved it to the cloud. In this case, Azure Data Warehouse, but where you use column store indexes, and they look a lot like Parquet, but right now I'm also using a lot of Databricks, and one of the native formats in Databricks is the Parquet format. Databricks is actually based on Spark clusters, and they don't have storage. You just connect it to whatever you want to. But it's really common to use the Parquet format there. But, oh, yeah, so that's how that works. So this is what an actual Spark cluster looks like, if it was built in the 80s, I'm guessing. Who was a Spectrum person when they were younger? Only the old people are raising, what is a Spectrum? I'm a Commodore 64 guy when I was younger. Got a thumbs up there, yay. This is basically how Spark clusters work. We're not going to talk a lot about Spark, but it's basically you have a compute engine like you would have a SQL server, but it does not have storage. You just connect it to whatever you want to. And a Spark cluster is always many of them. You have one central node, and that divides the queries on a lot of the other nodes. And you get the power of multiple machines, CPUs and memory that do the work for you. It's not just one, it scales out really nicely. It doesn't scale, yeah, it scales up as well, but you don't have to. If you want 60 machines, fine, works as well. Just create more nodes. This is obviously a bit me trying to be funny with a tape deck in there, but imagine those are Azure-based Spark nodes, or Amazon, doesn't matter. And you have blob storage there where your files are stored. Now, how cool is that? What kind of files do you use? Well, with Spark, but there are more systems, but I'm talking specifically about Spark because this is what I know best so far. You could just read CSV files. Nothing's going to stop you to put 60 terabytes of CSV files on your blob storage and read it with a bunch of Spark clusters and have fun. You can, like I'm doing here, I just say, okay, here's a bunch of CSV files. In this case, it's just one. And it has a header, and I don't know what the schema is. I don't know if there's date columns or something. I just want you to read everything the first time, make a schema, and then read everything again, and just show me the result. Sounds awesome, but a little bit, the overhead sounds a bit scary as well, right? And you could be thinking, okay, but we were talking about databases before, and now you show me how to read a file. I want to write SQL, right? I want to write a query. Well, that's not a problem at all. These things do this. You can query CSV files. You could build your whole data. don't do this, by the way. Don't build your whole database on CSV files. But you could, if you wanted to. This is how these things work. So you can write a query on top of CSV files, and these Spark clusters use something called Spark SQL, which looks a lot like T-SQL from SQL Server. There's a few differences there, but you'll catch up quickly. And you can run queries on files. Now, obviously, my example is a bit silly with CSV files, but it's just to get the point across that you don't really need a database structure with indexes and everything to build out a big storage layer on data that doesn't have to be inside a database. It could be based on files. Now, this is the first optimization that they're doing. You can compress the files, and as long as the compression is gzip and the file name ends in gz, it understands it. You can just say, oh, okay, just take those one file, a directory of files, doesn't matter. It will just grab the file, uncompress it, read it, parse it, you can run queries on it. And that's already a 10x improvement in the file size, and file sizes mean less I/O. I/O is the slowest part in these things. All good, right? So, even better idea. Let's take our 60 or 80 terabytes of, or hundreds of terabytes of data, put it in CSV files, and then compress them, right? Could be a lot faster. Only problem here is, it's an optimization on the file size, but not on the processing size, because now it's compressed, so you can't divide it anymore, right? These Spark nodes, they have there's many of them, and they cannot take the file and divide it amongst each other and go, you take half the rows, you take half the rows, and go process it with all of us together. Because it's compressed, you can't do that. You have to uncompress it first and then divide it. So one of the nodes has to do the uncompressing. So that's a disadvantage of doing it that way. Now, there's a few issues there, like I mentioned. There's no schema, only column names, so you have to parse everything every time you use it to get to the schema. You have to do the uncompressing on one of the nodes. You have to read everything all the time because it doesn't have any indexes, right? If you do a query, like count this group by that, where year is this year, it doesn't know which file has this year's data in it. It has to read all the files. So you're processing, if you have a terabyte worth of files, you're processing a terabyte worth of files for every query. Microsoft is going to love you, right? And there's no nesting possible. It's CSVs, right? It's only flat data. So there's a few problems that we have that we need to fix. Now, there is a fix that you can already do with CSV. I'm getting to the Parquet part, don't worry. There's a problem that you can fix with the CSVs already by having to read everything every time. Is, in this case, Parquet knows how to partition it. And it partitions it by putting the data in directories where the name of the directory tells you where it is. So, like right here, can we see that? Oh yeah, so I've partitioned on genre, which was a bad choice because the genre was a comma-separated list of things, but oh well. And if you did, for instance, a partition by year, and you would have directories called 2021, 2022, all these stupid years that we've had lately, that we're going to forget soon, right? It's so good to be here and look at people. And it would know, it would go, okay, now you have a column available in your queries when you do this. And Spark would go, oh, you said where year is 2022, and that's only that directory, so I'm not going to read the other directories. I'm going to skip those. And this is already a hint of where Parquet is going. It's all about skipping. It's all about not processing it if it doesn't need to. Now, we're still on CSV. So we fixed one of the problems by doing partition by. You have to pick the key well, though. You can only partition on one thing, right? You have one choice, so choose well. Date time is probably good. Very common, year, month, day, hour, like subdirectories. That works really well. You don't have to create the subdirectories. It does that for you. So if you query that, and this is an example in Spark, doesn't matter. There's multiple tools that use this. Things like Snowflake also use something similar. Where if you do group where genre is action, it just reads the one file because it's in one file. Even though I have a bunch of files for the whole table, it just knows, okay, just that directory. I'll just read that one file that's in the directory. All good. Another problem that we have is something that we really cannot fix with CSV, because it's a row thing, and there's no nesting possible. So if we have nested data, that doesn't fit in CSV. Databases have that problem as well a little bit. It doesn't really understand nesting, right? Unless you use JSON queries on top of a column in a database, and I see it all the time, way more. I thought we finally got rid of XML in columns, and now I see JSON everywhere. Oh well. So what do developers do to fix these things? They switch to JSON, right? JSON scares me, hence the, hence the picture of. So, still not on Parquet files, but JSON can fix this problem as well. And JSON can do the same thing. You can store things in JSON, partition it by a column, compress it, and you still don't need a database yet. But there are better ways. And one of these better ways that works really well in Parquet, and you may have heard this from SQL Server as well, there's something called a column store index. That's what Parquet does. It fixes a whole lot of these problems and more, but it also stores all the data not in a row. It stores it per column. And that logically still looks like a table with rows and columns. So you just read from it like it's a row store. You can still query it, and for you it doesn't matter. It still looks like something that has rows and columns. The SQL statements are the same. You don't have to have any specific SQL knowledge or Python knowledge or whatever to talk to a column store. It just presents itself as a row store, basically. But what it does, and this is just one of the steps, we'll get to many more, is store everything in order of all the columns that, like you see in the bottom, you see row 1 is stored like column A, column B, column C, column D, row done, next row. In column store, they do all the A's, and then all the B's, and then all the C's. How is that useful? How does that help you? Well, in the beginning, not that much. It's just a different way of storing things, but it opens up a lot of possibilities, and that is what the Parquet format uses a lot. Parquet was born out of a cooperation between Twitter and Cloudera. The name is it comes from a format called partition. I have to cheat and look. Partition attributes across. That was based on a white paper done by the Anastasia, David DeWitt, and Mark Hill, and SQL Server people might recognize the name Dave DeWitt. I don't know if you recognize the name, but he's been a keynote speaker at the PASS Summit in Seattle a lot, and he's well known in the database community. And actually, the column store format inside SQL Server comes from the same white paper and the same structure. Now, how does that work? Finally, we're getting to it. This is what the beginnings of a Parquet file look like. It starts with par1, it ends with par1, and all the data is in the middle, so the Parquet reader knows that this is a Parquet file. If you open one up, it actually reads par1. It's what it says. There's also a Parquet 2 format. We'll talk about that a bit as well. Now, the length of the footer is the first thing that you read from a Parquet file, and you start at the bottom. So the readers, you don't, the reader does that. But the readers start at the bottom of the file, then read the last 8 bytes, because par1 is 4 bytes, and then the 4 bytes before that are the length of the footer that comes on top of that. So they look there first, how long is your footer? And then they read the footer. Why is it not in the header? Wouldn't that be easier? Yes, for reading maybe. But for writing, it's easier to write the data, and when you're done, write the footer with the metadata and be done. You don't have to open up the file again, because now you know how much you wrote, and then put the header in to say where the data is, right? So everything is in the footer. So there's the metadata in the footer of the file. And the metadata, we're not going to go into much detail, but the metadata is according to a standard. It's called the Thrift Compact Protocol. It's an open source standard that will have all the metadata on where the data is in the file. Because now it's stored per column, that it's only useful if you know where the column is, right? Where does it end? You have all the A columns here, and then the B columns start. And if you need the B columns, you have to know where they start, because it's not a row-by-row thing anymore. So there's a lot of metadata to tell the reader where are my columns. The cool part is, if you do in your query, if you're being specific about which columns you need, it can skip the others. It doesn't have to read them. Another thing that is really useful in the metadata, it has min-max values for all the sections of your columns. So it divides up the file in sections, and it has min-max values for all of them. So if you say where column X is 150, and your min-max values are 200 and 250, it doesn't process that part. It just skips it. So now we're getting somewhere, right? You can partition by directory, so it doesn't have to read the whole file, it just skips the file. And based on your query, it can go into the file, read the metadata, and then decide what part of the file to process. So this is already helping the system not read everything. This is what the CSV cannot do, right? So this is what they look like, and it's actually a hybrid model. So it's not like the whole file is stored column by column. It has row groups, and the row groups have column chunks where the columns are, and then they have pages. Sound familiar? Pages? Pages, it's like a database, right? But based on files. And it has pages that contain the data. And we'll get to the dictionary page. But that's also a thing that can save the system a lot of... What just... Is it back? It's back. So now you have chunks of data in the file, and there's metadata on the chunk, so it can decide, oh, do I read this chunk? Do I not read this chunk? Everything is in groups of columns, so you can also decide to read or not read those columns. So now we have a format where the reader of the format can go into the footer and decide which parts to process or read. If the file system supports reading only a part of the file, even better. It can just go, I just need this little bit from byte here to byte there, fine. If it doesn't, it can read the whole thing, but decide not to parse specific parts. And it just, okay, I'll skip those. I've read it in, but I'm not going to do any parsing. I'll just throw it away. Depends on your file system. So these pages have metadata as well. So there's metadata stored in two places, in the pages and the rest is in the footer. And there's also a storage format that will tell you about the repetition levels, and those are for nested columns, so it knows how deep it is. This is a built-in standard way of doing multi-level, like the JSON stuff. It will just organize this for you. And then there's definition levels that it uses to store all the nulls. That part is just for the null values. It doesn't store the nulls in the data. If your columns are, if you have a column in a section that is completely null, it will just say in this metadata layer in the definition level, they're all null. I didn't store anything in the page. They're all null. There's no need to store that. So it doesn't store 1,000 nulls or something. It just says this section has only nulls. And then there is the encoded data itself. So encoded, that's not encrypted, or compressed, sorry. It's encoded. So what is that, right? We've been here, page header metadata, okay. There's two locations for the metadata, I've been there as well. So we're getting there a bit. There's metadata is at the end, so you just have to read everything, write everything once. You can just keep on writing metadata at the end, close the file, done. So faster on writing. Where the columns are in the file is known by the metadata, so you can just parse the metadata and grab only the data that you need based on your query. So it is really helpful if you don't do select star in your queries. right? That's a bad thing for normal SQL Server. For this stuff, it's even worse, right? And it gets worse. We'll get to that as well. Parquet tables, Parquet files, they're usually a bunch of files, because if you have 4 servers in your Spark nodes and they have 4 cores each, there's 16 processes that will process your data, and when they're done, they just write their own part, so you get 16 files, or 60, or 256, or whatever. It doesn't need to write just the one file. It just creates a directory, bunch of files in there, done. And here's the trick on the compression. The data portion, so not the metadata, is compressed. So if you see a gzipped Parquet file, it doesn't have to take the whole file and uncompress it. That's just the data portion. So it can still go in there, read the metadata, and then decide which parts it needs, just get those parts and uncompress those. That's the trick there, where it, like the CSV file, the whole file was compressed, so it just had to, it doesn't know what's in it, so it has to uncompress. In Parquet files, it's only the data portion that's compressed. So it can be specific there. Now the encoding part. And this looks a lot like the column store. The part 1, the Parquet format 1, version 1 is actually almost the same. What they do is plain encoding. That just means, well, if a column is 50 characters long, but you're only using 8 characters, I'm just going to say how long it is and then store just that. I'm not going to store all the spaces. Sounds really silly, but that's what it does. And this is the funny one. You start on the left with the actual data. So it's a Sony PSP, Xbox, Sega, then 3 times Nintendo Wii. So it compresses that by taking a special part. It uses a special page for that, and it builds a dictionary. And just say, and column store in SQL Server does somewhat similar. And it will just say, like, for instance, the Nintendo Wii just gets number 3. And then I'm going to store 0, 1, 2, 3, 3, 3, 4, 4. And then it compresses that down again as well, where it just goes, I have 0, 1, 2, and then I have 3 times the number 3, and I have 2 times the number 4. This is how it compresses it even more. And it then also uses the data type that it needs to store the numbers. So like the 0, 1, 2, 3, 3, 2, 4 fits in a few bytes, and it does that really well. It just keeps compressing it down. And this is one of the reasons why compression works well if you have it stored per column, because the types are the same, the data is similar, and there's probably a lot of repeating values in there. So that's why this works. This wouldn't really work on row-by-row compression. But now we're using column compression, you can do things like this. Big difference with column store. In SQL Server column store, if you have, I think it's 16 megabytes for the dictionary, and if it's full, it just stops writing to that chunk and creates a new, it doesn't create a file, but a new chunk, basically, segment, or what is it called. So you can get bad compression, you get lots of small pieces. In Parquet, it will stop compressing with dictionary and just switch to simple. And the rest will just be simple compressed, but the file size will be the same. The number of rows will be the same. And you can tweak and tune that a bit if you want to. You can say, okay, I want the dictionary to be larger, or you can say, I want the pages to be smaller. So the it will fit in the dictionary. If you have a lot of different values in there, and it would just create a huge dictionary, you can tweak that a bit. Or sort your data before you write it, right? If your data is sorted, it would compress it. The dictionary problem would still be there, but the repeating values problem would disappear a bit because you've sorted it nicely. Now, so can you sort only by one column? No, you can sort by as many columns as you want, but this might be a maintenance nightmare because you take your first load into the system with like 100 terabytes or something, and you sort it. Let's pretend you have lots of compute power, and you sort it, and everything compresses nicely. But then new data comes in, and you sort that as well, but it's only the little section, so it almost fragments, and you can improve that by rewriting it again when you're sorting it. So it's that sorting might help you with your initial load, but then you can have fragmentation, so you have to be a bit careful. Yeah, so exactly, you need to know what, so when you do the sorting, you need to know what your data looks like, so you can make a smart decision on how should I sort this. Maybe that's just too much work and you don't want to do it. If you sort it on one column, that might mean that another column, because you have to keep the rows together, right? So if you sort on one column, that might mean that the other column gets less interesting to compress, and you need to decide what's the best combination there. So you can only order for one column. Well, you can use multiple columns to do the ordering, but only one order, yeah. You cannot say, I want this one ordered this way and then that one ordered that way. That doesn't work, because it's like having an Excel sheet where you go, I want this one ordered A to Z and that one Z to A. That doesn't work. You have to keep the rows together, right? Or else you would lose it wouldn't know which row it is. So also when you query this, it has to, and you do it on two columns, and so the system needs to uncompress it basically until it gets the same value. And the first column might go, okay, I have 2 rows of the same, 5 rows of the same, and then there's the value that I need, and that's the 10th record. And then the other one is compressed differently, so it has to parse it until it finds the 10th record. So it has to do all the parsing on every column individually to get the row that you're looking for. So this is why it's even worse to do a select star, because it has to find the correct row, and they're all compressed differently, right? There might even be different compression algorithms. This is the cool part of the Parquet format, and also the danger. Because the rows are all the same type of data, you can use different compression algorithms. It doesn't have to use the dictionary compression. There's other mechanisms that it can use. But for uncompressing, if you did a select star, it will have to use all of them to get to the right row again, right?
So, just to make sure, it can read one row very effectively, but it doesn't like to read hundreds of rows, thousands of rows, millions of rows.
Oh, can it read one row effectively, but it doesn't like to read hundreds of rows? Sort of kind of the other way around. If you just select one column or 2 columns, it can read them really fast because it just uncompresses the whole thing in one go. But the more columns you need, it has to do that on all these columns to know where you are, right? It needs to do that and get the same column for the same row. It still has to present it to you like it's a row. So, but column A could be on the 3rd row because it compressed the first 2 into one, and column B could be the 6th row because it was compressed differently, and it has to do both of them and then go, okay, these all belong together. So there's a penalty for saying I want everything. But if you're specific and say I want this column, that column, and order by that column, it just doesn't. It also does not read the other ones, and it only has to uncompress. It's not compression. Decode. Let's go with decode. You can tell I'm not my language is not English, right? I have to find words sometimes. We could switch to German. Never mind. So there's a. Where are we on time? Okay, 15 minutes. There's a V2 as well that has some interesting things. For instance, instead of going Xbox is 4, so it does 4 Xbox. It just takes all the numbers of lengths, puts them in the first section, and then sticks everything else together, so you know exactly where in the string you need to be for the values. And now it basically did a column store compression on the length of the thing, right? Now you can treat the first part as an array of integers, and the second part as as a big string, and compress it all in its own way. So you can get creative here. I say you, but it's the engine that gets creative, and you don't know what it does, right? You don't have a choice. Maybe you could write a driver where you can be specific on what you want. If you have a very specific use case, you write your own driver, as long as it's a valid Parquet format. It works. Here's an interesting one. So you have the numbers 7, 5, 3, 1, 1, 2, 3, 4. And what it does, it stores the delta, so -2, -2, -2, 1, 1, 1, 1, and then stores the first delta, and then the deltas based on the first delta, so the difference of the deltas. So you get 0, 0, 0, 3, 3, 3, 3, which are lower numbers, and it can encode that quicker and in less bytes. And it works better on CPU caches and whatnot. My brain melts thinking of how would that be faster, I don't know. But somebody's thought that this would be a lot faster. It has a really interesting use case, though. If you have, let's say, an identity column, so you have 1, 2, 3, 4, 5, the delta is 1, 1, 1, 1, so the first delta is 1, and then the difference of the deltas are all zeros, because the first delta is 1, so it's the difference of the first delta, basically. You don't have to store the actual values. You can just say, I have 5 values, and the first one is 1, and the minimum delta is 1. That's it. It doesn't have to store any values. Here's the ordering problem again, right? So if I order on the identity column, and there's no gaps, and it all increases by 1, amazing compression, but what about the other columns? Right? They might be in the completely wrong order, and you'd be way better off to pick another column to compress on. Luckily, we don't have to think about this. Yeah, okay, we'll go back here. Luckily, we don't have to think about this because I've looked at conference videos from 5 years ago where they say, this V2 has been invented a long time ago, but I have yet to see an implementation. I'm thinking, okay, this is 5 years ago, so let's see how it is today. It's like IPv6, right? We all panicked 10 years ago, like, we need this because we're running out of IP addresses, and then nothing happened, right? Who's run into an IPv6 based website? I haven't. You've seen one? Okay. I've seen it. We had a broken router a couple of weeks ago, and it only handed out IPv6 addresses and no IPv4 anymore. So we noticed that everything broke except for Facebook. So Facebook seems to use v6 and the rest not. And who uses Facebook these days? Anyway. So you learn some random things here. Dictionary pages are always plain encoded. Delta encoding with the signed integers is called zigzag encoding. I have no idea how it works. I just thought it sounded way too cool not to mention this. Makes me sound so smart. Oh, this is zigzag encoding. No idea how it works. So the row groups, they have some sizes. For you, it doesn't matter. You can tweak these things, but most of these settings, if not all, these days are, if you look at old videos for Spark tuning, they say, oh, you have to switch on the compression and you have to do this. And no, you don't. It's all on by default. All the compression is automatic. Out of the box, for instance, Databricks, it has all the smart settings in it. It works pretty well. And tinkering with it, you're probably better off figuring out what your partition key should be, if any, right? If you're in a data warehouse and you read everything every time, why would you partition it? You'll just get more files, because now it has to chop it up in various directories. So you get more files. So you might do more processing instead of less. If you don't use the partition key in a where clause, then why would you partition by it, right? You just get more files. There's no need. So like I said, is V2 the future? No, maybe, I don't know. But if you're tinkering with Databricks or using Databricks, for instance, there's a lot of other tools out there that use the Parquet format, even under the covers. that you don't see, or even column store in SQL Server. That's not the Parquet format, but the compression algorithms are the same. So the problems are the same, and the profit that you have from using them is the same as well. One thing I discovered though is a SQL Server column store thing. That 80 terabyte, a couple of hundred terabyte, 80 billion rows thing that I had with the index lookups, I moved that to Azure Data Warehouse, and I kept the non-clustered columns, the non-clustered indexes to really fast find the row that I need. And then I wanted to go to the column store to get me the rest, like a clustered key lookup, right? That you get. It needs to go to the main index to find the rest of the columns. That is really slow. That just really doesn't work. Single row lookups on a column store index, don't. Don't do that. I seriously went back to a normal clustered index and two non-clustered indexes. Just basically moved my design that I had on-prem to Azure Data Warehouse, and it works like a charm. I don't have to talk to any SAN teams anymore. There's 3,500 users on that system now, and it works really well. Even though in Synapse they say, you can only have 50 queries at the same time. If they're tuned well enough, it works. You get that users working. Oh yeah, Delta. Can I talk about Delta for a sec? Oh yeah, I have a few minutes left. I can talk about Databricks Delta. Databricks Delta is it's a fancy name. It doesn't store differences automatically or something like the name would suggest. It's basically Parquet files with a transaction log. So you can update rows or delete rows or insert rows. That's not possible because it's all compressed, right? It wouldn't know where to put the row. It has to rewrite the whole block. It's like updating a zip file. It's not possible. You have to uncompress, change something, and compress it again. Same with Parquet. Once written, read-only, right? So it just writes the file again and then keeps in the transaction log like, okay, now this file is the main file with your latest records on it. So it rewrites the chunks. So that helps doing merge statements on Parquet, because you just use Databricks Delta. And a really big advantage, we already talked about basically Parquet files being, if you compare it to a SQL table, this is, you get a table scan every time. There is no B-tree index. It can't go to the correct spot right away. It doesn't know where everything is. That's where why all these files have metadata, so it can skip things, and you get basically a really fancy table scan because it knows how to skip things. And that is what Databricks Delta even improves, because they have statistics in a separate file on all your Parquet files. So now, like with the directory partitioning, it has min-max values on all your columns from all the files, so it knows which files to process. Databricks Delta has some specific tricks on allowing you not to read the whole file. It doesn't have to open up all the files and just get a specific part. It knows how to skip those things. I think, not an expert on that, but I think Snowflake even has a separate engine on top of the metadata to do really fast caching of all these min-max values of all the separate files that they use. So they can go really, that's why Snowflake is so fast, and probably maybe also so expensive, because they found something to make it really fast. This is also why column store in SQL Server, I just said it was read-only, right? You can't update it. So in SQL Server, the name is actually updatable column store. That's what they call it. But it's not what it does. When you update a row in a column store in SQL Server, it writes it into another table and doesn't tell you about it. And if you delete a row in a column store in SQL Server, it has a little bitmap index, and it just marks, I've deleted this row from this column store that I cannot update. And if you then query the column store, it goes, give me that chunk of column store. Let me grab the rows that you've changed, that you thought you changed here, but they're actually over here. And let me grab the deleted from the bitmap, and let me union this, and give you this like it is the column store. So it just, it cheats a bit. It just says it's updatable, but it's not. It just writes it somewhere else. And it will stay somewhere else and give you overhead. So it has to do that for every query. So if you didn't rebuild your column store parts or rebuild the index, not an index, you will get this overhead. So updating column store a lot is not really a good idea. It works, but it doesn't give you a good performance. So 3 minutes. How is this useful, right? Identity values. This V2 thing is not here yet. Identity values, maybe not a good idea to put in a column store because it compresses badly. Even worse, GUIDs. GUIDs are evil everywhere, and yet I see them all over the place, right? Where is column store? Because I talked about the Parquet format a lot. This is specific to Parquet, but the compression algorithms are used in way more technologies than Parquet format. Power BI, right? If you create a Power BI report, the compression algorithms in there, very similar. Column store, similar. Snowflake, similar. You see it way more than you think. So it actually helps to think about your data, right? How am I, can I partition? Do I really need to do a select star on all my data? If you're using Parquet now in Databricks, might be a good idea to go to Delta because it has better skipping of everything. Ordering of things, in Delta has something called a Z order, which is a good way to do partitioning without having to choose the one partitioning key. You have another one that you can pick. And there's some things that you can use just to help the engine skip stuff. There's something called a Bloom filter, which is, it says it's an index, Bloom index or something, I'm not sure. But it's actually a sort of statistical thing that will tell the engine, like, okay, I'm very certain that the data is not in these files, but they might be in those files. And it just only has to read the files that it might be in. It doesn't know for sure, but it can tell it, and can tell the engine which files it doesn't have, which files don't have that data, so it can skip. So, to summarize, Parquet files are just a really fancy way to do a table scan, and it can help you skip a lot of data if, me explaining how that works might help you to understand what's the magic behind it, and that it's not really magic. It just has a lot of metadata to help you skip stuff. And if you, thanks, 10 more seconds. I'm going to steal 10 more seconds. So if you're expecting OLTP type performance, not the right format. Don't use it for OLTP systems. It just won't give you the performance that you're needing. With that, if you have questions, I'll stick around here for a bit, but we're on time, so I'm going to have to stop. It's 6 o'clock, so it might be time for a beer as well. I'm just going to stop talking. Don't forget the feedback, and I hope you have a great day tomorrow as well if you're here. Thank you.